Okay, so here's an overview of the talk. And I'm doing things in a Roy G. Biv fashion here, so you can figure out where we are in the talk as we go along. First thing is I've got in red the preamble. So we're going to talk a little bit about what the IMF is and why it is important, why we want to study it. In yellow-orange here is building the 20 parsec census that we're going to use to build the 20 parsec IMF itself. Then in green, we're going to talk about the steps of building the actual IMF once we have the census figured out. Okay, and in blue, we've got the resulting IMF that results from that. We're going to talk a little bit about what that means. And then what it really means as far as a physical sense. So when we finally have the IMF figured out and we have an empirical visualization of it, what does it mean as far as the physics underlying star formation? Okay, so here we are, red preamble. Okay, and here is a a cloud of gas collapsing under its own gravity, forming stars. And this is done via hierarchical fragmentation, as you see there, down there at the bottom. And there's many things that can come into play here to shape how star formation actually happens as this cloud is collapsing. There are things like supernovae explosions for high mass stars that might go off while this star formation process is still going on. There are magnetic fields that could shape what happens within the cloud itself. And there could be protostellar flows from protostars that have formed and have these immense jets that go out and disrupt material in the rest of the cloud. I'm going to pick out two things in particular here that could actually shape the low mass end of the star formation process. And one of those is dynamical ejection of protostellar embryos. And you see this going on the animation on the left, where you have higher mass stars are forming, lower mass stars are forming at the same time. And you see that the lower mass stars sometimes get ejected completely out of the cloud, possibly while they're still trying to accrete material and form into larger objects. So this could be a way of stunting the growth, for example, of a young protostellar embryo. Then there's also photoevaporation. So if you have a cloud of gas that has formed some very, very hot O stars, for example, the winds from those O stars can ablate the accreting material that's still accreting onto a protostar nearby and rob that embryo of actually getting any larger than it is at present. So to recap here, we have higher density areas might have more dynamical interactions. For example, if you have an area like the Taurus molecular cloud that doesn't have that many stars in it, it's not very dense, there could be very few of these dynamical interactions that are slinging objects out of the cloud. But if you have an area like the Orion Nebula cluster, this might be going on quite often. And then second, there are regions with higher mass stars that will have more photoevaporation. So there are no O stars in the Taurus molecular cloud, for example. So you wouldn't expect this effect to be working at all. But in the Orion Nebula cluster, you would expect stars to be affected by the photoevaporation of the O stars that are there in the trapezium. That having all been said, we've known now for about 20 years that if we look at nearby clusters such as Taurus, the Pleiades, Orion Nebula cluster, and so forth, that the cluster-to-cluster variations in the IMF are modest or maybe not even there at all within the observational uncertainties, at least above 30 Jupiter masses or so. And this was reiterated in an annual reviews article by Bastian, Covey, and Meyer in 2010. And they found it was also true in the field and also in globular clusters. So over a wide range of ages and a wide range of conditions within the galaxy, the IMF looks pretty much the same, surprisingly enough. So this led to a couple of quotes I wanted to give here. One was by Estella Offner in her review paper from 2016, where she says the IMF is remarkably invariant across a broad range of environments within the observational uncertainties. And I don't think I've heard anyone say it quite as succinctly as Mike Grudich did at our Milky Way conference over at Caltech back in October of 2023. And he said, the IMF may not be universal, but it's far more robust than it has any right to be. Okay, this is actually good for this talk, by the way, because we can deduce the initial mass function from the nearby census, and it will retain imprints of the physical processes of star formation if the IMF is truly invariant across time and across environments within the galaxy. So despite the fact that this is a well-mixed sampling of the disk, it ought to still have imprints of the physics. And just to remind you, when you're talking about the nearby sample, you're talking about one that's largely solar metallicity. You're talking about one that's, if you're particularly as close as this one within 20 parsecs, is going to be reddening free. And it's going to be extraordinarily well characterized for multiplicity, better than any other sample on the sky. So we're really going to know what we're looking at in an individual star by star basis. Okay, here we are at the orange and yellow section. So building the 20 parsec census. Okay, we've had a long time to work on the 20 parsec census, obviously. I think the first spectrum of an M dwarf was taken in something like 1913, and the parallaxes followed shortly thereafter. So we've had about 100 years to start really cataloging the sky down to the bottom of the stellar sequence. And there have been compilations of nearby stars over the past many, many years. And the last one pre-Gaia was called the Catalog of Nearby Stars, and that was published in 1991. And I think it might actually have gone out to 25 parsecs. And then, of course, Gaia came along and really scooped it up for stars. I mean, we really know the stars within 20 parsecs very, very well, largely because of Gaia. For brown dwarfs, we haven't had quite as long a time baseline to work with. There have been all-sky surveys that started coming out in the late 1990s, 2MASS, and then later for WISE around 2010, that have really helped us characterize the 20 parsec census for the brown dwarf component. And there have been various compilations of brown dwarfs that have happened over the years. We tried to keep one at IPAC called Dwarf Archives, and we finally gave up in 2015 because there were so many brown dwarf discoveries we couldn't keep on top of them all. But we do have old data we can go back to and sort of start drawing to create this 20 parsec sample, so I had to do it from scratch. Okay, so I'm going to jump ahead a little bit here and tell you that the 20 parsec census, once we have everything properly cataloged, has 3,600 objects in it, more or less. And that's a good sampling. It gives us the ability to bin up into smaller mass bins to look at little details in the IMF. But 3,600 objects is a lot to have to go through individually. And if I had to pick a larger radius, I probably would still be working on this paper today. So if I wanted to go out to 25 or 30 parsecs, I probably would have been driven mad by now, actually. Okay, but it turns out 97% of the objects in this sample have parallaxes with less than 10% error. And because of Gaia, many of them have errors much, much smaller than this, in fact. And of those 97%, 65% come directly from Gaia. We have another 19 or so percent that get into the sample because they have an association with a Gaia source that already has a parallax. And there's two ways this can happen. First is you have a low mass companion to an object, a brighter star in Gaia, and the brighter star itself has a parallax in Gaia, but the companion is too faint. Well, we know from other surveys that those two objects are actually co-moving in space. So we get a parallax for free of the secondary because of the primary. And it can work the other way around too, in that the secondary is detected in Gaia, but the primary is too bright for Gaia. So we can do the same thing, and we pull in the parallax for the secondary for the primary. Well, there are other primaries in Gaia that don't have a secondary. They're just too darn bright at all. And we pull those in. It's another 2% or so from Hipparcos. Then that leaves the brown dwarfs. The brown dwarfs are not visible largely in Gaia. A few of the L dwarfs and a few of the T dwarfs are. But for the rest, we had to do parallax programs from the ground and space to do those, and that was another 7.3%. And then for the last stragglers on that we got at the very end of before we published this paper, we got another 6% with Spitzer parallax follow-up, which is shown there in the lower left. And on that point, I want to bring up the first thing I'm going to say about citizen science. So citizen science played a very important role, and this is particularly through the NASA Backyard Worlds Planet 9 citizen science project, to pull out those candidates from WISE and from NEO-WISE sooner than the astronomical community could do it, because we were about to have Spitzer mothballed. We really wanted to get as many objects on the Spitzer parallax program as we could before we lost Spitzer. And the citizen science project enabled us to do that. So I give big kudos to those folks who, of course, ended up on many of our papers as a result, but they made that possible. Okay, as I mentioned earlier, we want to build the initial mass function of individual objects. And that means splitting the multiple systems into each one of their separate components. And this is really the hardest part of the exercise because it involves a lot of this. Doing a deep dive into the literature on each system. And I'll get back to this in just a second. Once you've done that, and I'm giving an example here of the Xi-UMA system, you need to break that into its separate components and try to characterize each one of those components as much as possible so you can eventually get a mass estimate out for each of the, in this case, 5 objects in the system. So you want to pull out spectra, photometry, whatever you have in order to characterize those objects. And then finally, once you've characterized each component, you can assign it a mass. Okay, on this first, unresolved systems.
The binaries that you cannot resolve them, that they are actually binaries and they may bias, right? There's some maybe not negligible percentage of binaries.
Yeah, so in cases where we have other data on the binary, like a delta magnitude from some AO program or something, we go ahead and use that to try to split the components out. But if it's a binary system where there's absolutely no other information about what the other component is, there's no delta magnitude, we just maybe have a high Rui value from Gaia, we leave it in as a single star for now. So we don't try to guess what the secondary's mass is or the primary's mass. We just put in what we think it would be if we had just a single star there. Okay, so the second point I want to bring up about the role of citizen science is actually in this deep literature dive. And there I decided I really didn't want to go through ADS for all 3,600 systems by myself without a little help. So what we did was we set up something called the Stellar Ambassadors Program for citizen scientists on the Backyard Worlds program. And said, if you want to come in and be the ambassador to Aldebaran or whatever, what you will do is you will go into Google, Wikipedia, ADS, whatever, and find out all you can about Aldebaran so that when you're sitting on the Aldebaran Council as the contact for, the sun, you don't look stupid. You don't want to say, Aldebaran has a secondary? I had no idea. That would be really embarrassing, right? So they went in and did whatever they could to try to figure out what is known for each one of these systems as far as the number of components in it. Maybe it's got a couple of planets, maybe it's got 2 stars, whatever. And I realized when we started this is going to be an inhomogeneous mess, right? Because everyone's going to do things slightly different. Some people would find the second component. Some people would not find the second component in the system. But what I asked them to do is write down the sources of their information. And this ended up being the key, because I saw some of the same sources of information coming up over and over and over again. So I started with those sources for my deep literature dive and then did the deep literature dive after that. And by the time I got to the single object by single object search, I had most of those already figured out from the sources that they had identified, which was really, really cool. Another thing happened, which was quite serendipitous, and that was we had one of our citizen scientists who calls himself an independent scholar. This is Kevin Apps. He came to us and he said, I got a master's in astronomy and I kind of dropped out because I really didn't like the research part. But he said, I've been keeping this catalog on my own time of all the stars within 100 parsecs of the sun, and I'm pretty sure it's complete within 30. Would you like to take a look at it? I'm like, oh, yes. And he came up right about the time I was finishing this. So we were able to compare my list to his list. And I had some things he didn't have in his census, and that was because these are largely unpublished brown dwarfs that I knew about. And he had some things in his I didn't have in mine because he's been doing this for years and he goes through AstroPH every single night and updates his database. So this is like the teacher's version of the book, and I had the answers in the back. So anyone who wants access to his census, just let me know and I'll give you his contact information. He doesn't want to publish it. He just wants to help people. So he helped me quite a bit. Okay, so with that in mind, I had what I was pretty sure was a pretty solid 20 parsec censuses and as complete as we could currently make it. So now let's try to build the initial mass function from that. Okay, so wherever possible, we try to use directly measured masses. And for multiple systems, if you have the right kind of multiple system, for example, in an eclipsing binary, we have radial velocity information. You can get the direct mass out. And there's several other ways you can do this, like binaries with acceleration, astrometric binaries, et cetera. There are 157 components within 20 parsecs that have direct masses that are in multiple systems. And you can also sometimes do this for single objects. There's gravitational lensing, and I think there are 3 objects within 20 parsecs that have had their masses measured by lensing. One of those is Proxima Centauri, and there's a couple of white dwarfs that have been done that way. And then there are a few higher mass objects whose masses have been measured directly using astroseismology. But if you add 157 and 18 together, that's not 3,600. So we still have about 3,400 objects that we have to somehow get masses for. So how do we do that? Okay, now we're going to take sort of a back up and look at the big picture view of what the 20 parsec census looks like. These are only individual components here. There should not be any doubles unless they're ones we have not resolved yet. And this is just showing the absolute J-band magnitude on the y-axis versus J minus W2 color on the x-axis. And the thing to notice here, these are color-coded, by the way, by spectral type. The 20 parsec census spans 30 magnitudes in J-band. And here's a little bit of a preview of what the IMF will look like towards the end of the talk. So if you look at the brightest object on this HR diagram, it's the primary in the Epsilon Scorpii system, and it's a K3 giant, sorry, K1 giant. And it's at 19.8 parsecs. So it's right at the very edge of the 20 parsec census that we're considering here. So in other words, this object is a pretty rare beast. We had to go all the way out to the edge to find one. On the flip side, down here in the lower right-hand corner, there's that object that has a J minus W2 color of 11. That is the 250 Kelvin brown dwarf WISE 0855 minus 0714. It's at 2.3 parsecs. It's like right here. So we didn't have to go very far out at all to find something that cold. So that gives you an indication of what the IMF is going to look like in the end. Okay, so back to measuring masses. Here's the main sequence. We know the main sequence has a mass-luminosity relation, so as long as we can characterize the luminosity, we can estimate the mass for those objects. Here's the brown dwarf sequence. There's no such relation for those because you have to also know the age. So I'll tell you in a few slides more how we do the masses for those guys. There's evolved stars, of which there are a few up here at the top. Those have to be handled separately because you can't use the same relations to estimate the mass for those. And I'll tell you how we do that in just a minute. Then there's the white dwarfs that are even more evolved, and that involves a little bit more work to get their masses as well, because there we want not their current mass, but the mass they had when they were on the main sequence. Okay, so here's 3 more views of what the HR diagram looks like for the 20 parsec census. This is absolute magnitude versus G minus W2 color. And notice in that one, we don't go very far into the brown dwarf regime because these are Gaia-based colors and magnitudes. On the middle one, we have a W3 magnitude from WISE versus spectral type. And you see this nice chimney of objects here, which are the objects that are climbing up the red giant branch, which is pretty cool. And then on the far right diagram, we see more of the brown dwarfs this time because we're using WISE W2 magnitude versus J minus W2 color. But that's what the 20 parsec census looks like. Okay, so main sequence stars, how do we actually get the masses for those? So for K and M dwarfs, there's this well-known relation where if you use absolute K magnitude, the relation with mass is actually shows less scatter than any of the other absolute magnitudes you can use. And this has been known since the days of Delphos back in the late 1990s. But we use this relation from Andrew Mann's paper from 2019. They uses binaries with total mass measurements, but there's a Sinai ambiguity in those. So they did a little bit of Bayesian wizardry here to make this, this plot. But this is the plot we use for anything that has a KS magnitude in our 20 parsec census. Unfortunately, not everything has a KS magnitude, so we have to do some other things. So if we have a GBP minus GRP color from Gaia, we can actually use that color to estimate an effective temperature for the main sequence star. There's an effective temperature to mass relation from the work of Torres et al., which uses eclipsing binary measurements. And that relation goes from late O all the way to mid M. So as long as we have a Gaia color, we can use that relation to get a mass estimate out for our main sequence star. Well, there's some objects that don't have KS or a Gaia color. But if they do have, for example, a capital G magnitude from Gaia, then we can use this relation from Chantos to do something very similar and get the mass estimate out. And then for others, we are looking at the Starhorse database, so the compilation of results from the Starhorse code in Anders et al. And that uses broad wavelength photometry to actually compare to the models and actually make a mass estimate that way. And there are a few objects where we can't use any of these methods because they're either not in Anders or they don't have any of the photometry we need. So we use whatever data we have to estimate a spectral type. And then we use this very, very crude relation from my paper to estimate what the mass would be based on that spectral type. Okay, brown dwarfs. Brown dwarfs have to be handled separately. As I mentioned, there's no mass luminosity relation, but there is a mass age luminosity relation. Unfortunately, for most of these, we have absolutely no idea what their ages are, so that doesn't help at all. So we can't get individual masses, so just completely give up on that. What do we do instead? Well, what we do instead is we can estimate an effective temperature using their spectra and photometry over a broad section of wavelengths. Compare those to models and actually get the effective temperature out that way. And then you take the effective temperatures for all those brown dwarfs and see what the distribution looks like within 20 parsecs. So you have a histogram of all the effective temperatures for the brown dwarfs. Next step is to go in and build a bunch of predicted effective temperature distributions. And this way you can build them based on various assumed initial mass functions, whatever you want to pick, log normals, ones with power law exponents, et cetera. You can pick different birth rates within the galaxy. You can pick different cutoffs for the low mass cutoff of brown dwarf star formation process. And then you pair those up with evolutionary models to get the mass, to get the effective temperature. And this is something that my high school student, Yadu Krishna Raghu, who's now an undergraduate at Berkeley, wrote as an APJ paper last year. And here's our result from that paper. And that is, of all the predicted distributions that we came up with, the one that best fits the empirical data is the one shown on the left here. The empirical data are shown with the black dots with the error bars, and this is just showing the space density on the y-axis versus effective temperature, bend in 150 Kelvin bends. And the best fit of our predicted T-effective distributions is shown there, and it's actually red, green, and blue, and the different colors show different low mass cutoffs. But we don't go cold enough in temperature to actually be sensitive to what the low mass cutoff here is. But you'll see that the best power law for the brown dwarfs is an alpha of 0.6. And the birth rate here just happens to be constant. Yes?
Pulling models for the brown dwarfs, right? This is a big question in the literature. And that you said that you had different evolutionary models. So I assumed that you tried different pulling models.
Right.
Which one actually worked?
The one that worked the best was the one from Salman and Marley, which is 2008. And that one is a hybrid model where they put together models with clouds and models without clouds. And the cloudy models are the ones relevant for the L dwarfs, and the non-cloudy models are the ones relevant for the T and the Y dwarfs. And those are the only models that predict that bump that you see there about 1250 Kelvin. And that's because the L dwarfs get cloudier and cloudier and cloudier. There's a lot of back warming in the atmosphere, and they're not cooling as fast. But suddenly those particles start to rain out of the atmosphere, and there's a rapid cooling process, and they go into the T dwarf regime that way. So those are the only sets of models that actually predicted that bump. We can rule out the rest. Yeah. Now that is a hybrid model, and it's a little bit not completely physical at this point because it's two things stitched together. So there's still improvements to be made there. Okay, white dwarfs. So these are a problem. So we want the final, we can actually measure, in some cases, the final mass of the stellar remnant, but that's not what we want because this is the initial mass function. We want to know what the initial mass was before this thing left the main sequence. That's really what we're after here. But what we'll do is we'll try to estimate the final masses of each one of the white dwarfs and then back out what the initial mass might be. So here we can get present day masses by doing one of two different methods. So if we have a spectrum of the white dwarf and it shows either hydrogen Balmer lines or has helium lines in its spectrum, we can compare those to the models to get the surface gravity and the effective temperature. And then using the cooling models, we can get the mass. Or if we have something like a DC white dwarf that doesn't have hydrogen and helium lines, or we just have broad wavelength photometry, we can take that photometry, compare it to the models to get surface gravity and radius, and the mass falls out directly from that. Again, that's the current day mass of the white dwarf, which is not what we want. But folks in the white dwarf field have been working for many, many years on building these initial to final mass relations using largely M dwarfs in clusters of known age. So if you see a white dwarf sitting in a cluster and you say, okay, I know from my models that this thing has been cooling for this amount of time, and I know the age of the cluster, I can just take the age of the cluster minus the cooling time to figure out what the main sequence lifetime of the progenitor was. And if you know the main sequence lifetime of the progenitor, then you can get the initial mass. So that's how we derive this. Notice the uncertainties on this are very, very large, though. So this is not an exact science. Okay, other evolved stars, and I'm pointing to two different. Yeah. Oh, should I go ahead and answer that? I can't quite read it, but yeah. So, do you have an estimate of how many? I didn't read it fast enough.
The white dwarfs missing is a cool beyond your census.
Oh, is they cool beyond my
Yeah,
census?
essentially, if they're older than, 8 billion years, they will be on cooling curves that may cause them to be undetectable.
I didn't think there were actually any white dwarfs that were cooling that fast, because that involves Debye cooling or something at that point, like a crystallization of the white dwarf. I don't think anything like that exists. Yeah. The most massive ones would. Okay.
Yeah,
That's news to me. Okay, thank you for that. I didn't realize that. Okay. I had several white dwarf collaborators on the paper and they didn't actually bring that up, so I'll have to ask them about that.
What's the faintest apparent magnitude of your white dwarf?
Off the top of my head, I would not know, but I think all of those are in Gaia.
So, do you think are they 20th magnitude, right up against the sensitivity limit?
No, they're definitely not that. Yeah. So I don't.
It seems like
I don't think we're missing any, unless there's something special about the really high mass brown dwarfs that I don't know about, because that's certainly not my subfield either. But
the high mass white dwarfs.
I think that's what the comment was about.
Well, why would those be dimmer than the lower mass white dwarfs?
smaller,
Physically smaller.
just physically smaller.
Yeah, but by
And they're cool.
enough,
And they cool, I mean, but presumably if you're not, the ones you have identified are not pressed up against your brightness, lower brightness limit, then, there'd be a big gap, and then maybe they probably are not very many that are not being affected. The one thing, you get a whole bunch right down to the lower limit of your luminosities you can access. The ones you have seen not near there.
I think that's the case, but this is an interesting comment anyway. Okay, so for the evolved stars, there are so few of these on in the 20 parsec sample, and these, of course, are the closest, brightest examples of evolved stars that we know about. These are very, very well studied. So we just went into the literature and checked what people had done as checks against theoretical isochrones to get out the initial masses for those. So that was actually pretty easy. And one thing I didn't mention on the earlier slide is that we want to have a handle on how much contamination we might have by halo stars and things that are low metallicity. Because if you're using solar metallicity relations to estimate the masses of your objects, you don't want to estimate the wrong mass for a low metallicity object that doesn't follow that relation at all. So what I'm showing here are all the objects in Gaia within 20 parsecs that have UVW space motions, which is the vast majority. And also shown in the background are the Gaia stars within 100 parsecs are shown in gray. So any of the objects that are within the blue dashed line there, or is what's canonically called the thin disk, anything that's outside the red dashed line there is something that would be considered a halo object, and the ones in between are thick disk. And that's sort of a cartoon model, albeit. But you see there's only, and the color coded is showing the 20 parsecs objects. So the ones that are part of the thin disk are shown in blue. 20 parsec objects that are part of the thick disk are shown in yellow. And those that are in the halo are shown in red. And there's only 6 objects total, one of which is Kapteyn star. So it turns out this contamination is not big, and it's not something we really need to worry about. But let's turn it over to the brown dwarf side. For brown dwarfs, what we did was we usually don't have radial velocities for these, so we don't have full UVW space motions. But we can go in and estimate where they would fall in this tomb ray diagram if we just assume a range of radial velocities. And I assumed a range of radial velocities from minus 200 kilometers per second to plus 200 kilometers per second. And these are only the brown dwarfs that are in the color coding here that appear to have some sort of low metallicity signature in their spectra, which would indicate they could possibly be part of the halo. And there's only 2 of these. that are clearly part of the halo, regardless of what the radial velocity might be. And those are the two on the far left. The SSPM 1444 object, which is a subdwarf L0. And then the object known as WISE 1434, which we have been lovingly calling the accident in the literature. It's a bizarre ultra subdwarf TY. We don't know what it is because there's only one like it in the sky that we know about so far. So again, the total of brown dwarfs and stars that are in the halo is only about 8 objects out of 3,600. So it's not a big contaminant. Okay, we're finally up to blue. Okay, resulting IMF. And some of you are going to hate this part because I've been talking to you earlier today and you don't agree with me on this, but I'm going to go ahead and say it anyway. Okay, I think there are preconceptions or misconceptions out there by people as to what the IMF actually is telling us and what the empirical data actually have been saying over the past many years. And I've seen this quote mentioned in many telescope proposals saying the initial mass function peaks at 0.3 solar masses in the early M dwarf regime. So let's talk a little bit about that. So people will show plots like this, and this is a plot showing the Pleiades mass function. And notice that both axes are in logarithmic scales here. So you've got the number density on the left, and then you've got the masses on the x-axis. But notice the masses are in logarithmic scale. But clearly the peak there is about 0.3 solar masses. There's nothing wrong with that. Okay, here's what the luminosity function looks like. And this is from a Krupa paper from 2007. And you see the luminosity function is peaking about an absolute V magnitude of around 12 magnitudes. And again, that's also at early M, around 0.3 solar masses. So that seems to reinforce the notion that the IMF peaks at 0.3 solar masses. And if you look at just the 8 parsec census within the sun, and this is quite old now, it's from 2008. This is just showing the total mass versus spectral type, but each one of those dots is an individual object. And you see there's 4 A stars, 1 F star, 5 G stars. Well, there's 92 M dwarfs and a trickle of brown dwarfs here and there. But it also reinforces the idea that, oh yeah, well, IMF peaks in the M dwarfs. There's no doubt about it. But let me remind you of this diagram that I showed earlier. So if you look at the M dwarfs, they are very, very steep on this diagram. They cover a wide range of masses. From M0 to about M4, you're covering 0.6 solar masses all the way down to about 0.1 solar masses. That's a lot of real estate right there. And I would say that if you're thinking about the power law in a linear sense, this statement is totally wrong. If you use this statement, you've got to clarify this is in log, not in linear. Okay, so here's the answer. This is what we get from the 20 parsec census. And I'm showing the high mass objects on the left, low mass objects on the right. So this is going from 8 solar masses down to 0 solar masses. And this is just the number of objects within 20 parsecs binned up in 0.1 solar mass units here. And there are a couple of things to learn from this diagram. One is that the universe loves to make low mass objects. Second one is the peak of the IMF has yet to be found if you're talking about linear units. Keeps going up and up and up. And there's another thing to keep your eye on, which is the whole point of going through all this and writing this paper was, are there signatures of the formation process in here? Ned, did you have a question?
Yes, I'm just wondering, what's the highest mass object that looks like it's 0 for a long way?
I'm going to zoom into this in a minute, and you'll see. Yeah. Actually, the highest mass. Initial mass we had for a white dwarf was around 7 solar masses, but there's a large uncertainty on that. Yeah. Okay, so here are the 3 places where there's an inflection point in the IMF. And you can see the top 2 if you really squint I'm sorry, you can see the bottom 2 if you really squint. The top one is sort of lost in the binning here, but I'm going to pull that out in the next slide. So let's talk a little bit about how we formed that IMF that you just saw in the last slide. And what is shown here in blue is the actual histogram of the mass estimates we got through all the processes I described a few slides ago. But now I've broken up the IMF into 3 different mass ranges here. So we've got 8 to 1.5 on the left, 1.5 down to 0.4 solar in the middle, and then the one on the right is showing 0.4 all the way down to 0. Now you can imagine, especially if you look at this object on the, this panel on the right, you see these peaks. These peaks are not real things. I mean, they're not real features in the IMF. These are secondaries. These are M dwarf secondaries to stars where I only had a spectral type guess as to what they might be. So you're seeing peaks here at sort of M2, M3, M4, M5, M6. And I just assign the same mass to all the M3s, all the M4s, and all the M5s, but it has a very big uncertainty on it. So what we did, since the uncertainty changes from object to object, this is not really a very accurate representation of what the histogram would look like. So we assumed a normal distribution and did some Monte Carloing just to pull out a random number from that normal distribution where the center is on 0 and has a standard deviation of 1. You pull out that number, you multiply that number by the uncertainty in the mass, and then add that back to the mass estimate I have. And you do that, Monte Carlo, each one of those, and build a new histogram. And you do that 10,000 times and average all those histograms together, and this is what you get. So a lot of that fake signal went away. And now we take this, which we call the real empirical IMF, and try to fit power laws to it. And this is what we get out. So what I tried to do here was to set it to the saltpeter IMF. This is alpha 2.3 at the higher masses. And then at some point, we'll take that out as far as we can, going to lower and lower masses until it looks like we need to change the slope. And we know from the literature that the slope is going to change to about an alpha of 1.3 at lower masses. And then from there on, we got to see if that will connect to the alpha of 0.6 that we get in the brown dwarf regime, or whether we need another piece in there. And it turns out we do need another piece in there. Yeah.
Your histogram was sort of to 0 after, I think.
Oh, yeah.
3.1 and 0 masses, but when you do the Monte Carlo on billing, you get like steep hikes.
I failed to mention one thing, and I apologize. So the blue histogram that you saw before was just the stars, because it's only the stars that I can get a mass estimate for. So I did the Monte Carloing only on the star part, and then I took my alpha of 0.6 from the brown dwarfs and just added it on to the end there, because it's already scaled appropriately. Yeah, sorry about that. Okay, so here are where the inflection points hit. That's where I had to change the slope of the IMF to get everything to work. Okay, and there's the alphas. Okay, so in the last section here, I'm going to delve into what does this mean, and I have no idea, but we'll find out. We'll see if you believe any of this. So, okay, so here again is the IMF as we found it from the 20 parsec sample. And I decided, we've known about this kink in the IMF around, 0.5 solar masses for quite a number of years. So let's see what various review papers have said about that. So I went to this 850-page book by Stoller and Poller from 2004 called The Formation of Stars. And tucked away on page 125, there's this great quote that says, "Unfortunately, current theory cannot explain in any convincing manner the form of the IMF." Like, oh, well, that's unfortunate. This is 20 years old, though, so maybe there's more up-to-date info. So I found another review, and this is an annual reviews article from McKee and Ostreicher in 2007. And they go through this entire list of all the things that any IMF theory needs to explain to be valid. And there's 4 pieces here, one of which needs to explain the saltpeter power law slope at high mass. It needs to explain that turnover slightly below that. Also needs to explain what the upper mass limit is and the lower mass limit is. And it also needs to explain why there's this sort of universal IMF across many, many environments. And they go on for the next 4 or 5 pages and say that the only one of these they have really good handle on maybe is C, which is what the upper and lower limits might be. Okay, we proceeded to later reviews, and this is by Stella Rothner in 2016. And she says a comprehensive predictive theory of the IMF remains elusive. So that's where we were in 2016. Fast forwarding to 2022, there's this paper by Guzjanov, which says that they've made inroads into modeling more universal IMFs. So they've gotten to the point where it's like, okay, we think we have IMFs that are invariant to a lot of things. And the things that are invariant to are things like stellar radiation, winds, and supernovae explosions. Those have no noticeable effect on shaping the IMF, but they do find that protostellar jets directly affect the amount of material that's getting accreted and just removing material completely from around stars. So, and this is where I'm really wildly speculating, because at this point, these kinks are probably caused by many different physical processes coming together at once. But let's just naively assume that this is where the protostellar jets really start having their influence known. So they're taking a certain amount of stars here and stunting their growth because that accretion material is flying away. Well, since we're being crazy anyway, let's say that this particular kink is maybe caused by dynamical ejections that are stunting the embryo growth. And then the next kink out here, where you see things going much stronger upward again in the brown dwarf regime, may be where all those stunted embryos end up in the end. I don't know. That's just pure speculation on my part. I would say this is the actual answer still, and I'll leave it there for questions.
Yeah, I was wondering a little bit more about what Smadar asked about earlier about how these like unresolved binaries can bias your mass estimates. So I was curious what fraction of your sample is in that like high Ruby category, and if you account for this bias at all in your IMF error bars or something like that.
There is certainly going to be, sorry, a bias in the IMF due to unresolved binaries. There's no doubt about that. And I did not try to correct that in the paper. What I did list was all the objects that had, I think, Rui values above 1.4, which is the sort of the canonical value that K von Stassen uses. And as I recall, there might have been something like 200 of those. I can't remember the exact number. And there's also a number that show accelerations. And that's just a smaller number of objects, but there are some accelerators in the 20 parsec sample where we don't know what's actually causing that acceleration, but clearly there's one or more members in those systems. So what I did there was I just took the information I had at hand and assumed there was one object in that system and estimated the mass just based on that one object. Oh, sorry.
Pradeep, with that?
Any observational study to look at like high velocity ejected low mass stars from like the 20 parsec radius?
Oh, in the 20 parsec radius, or?
Characterize the population of the stars that will be ejected from like this 20 parsec.
Well, people have tried to do that kind of analysis on star clusters where you're still very close to the star formation event itself and look at how many low mass objects have been ejected. And I don't have numbers in my head for any of that kind of thing, but when you're talking about the 20 parsec sample, of course, it's a very old, very well mixed, and it's been many cycles around the galactic center already. You know, we've been many revolutions around in the Milky Way. So that's a very well mixed population. The 20 parsec sample we have now will not be the 20 parsec sample we have 10,000 years from now. So it's not so much that objects are being ejected so much as they're just well mixed. So things will leak out of the 20 parsec sample, but other things will leak in, if you will. So it's constantly changing.
See, saw Smadara's hand up. What was your question?
So it's a follow-up on Isabel's question that we will follow.
Just a follow-up on yours, yes.
So,
I see where this is going.
well, what I was thinking is that to test the systematic that may arise from unresolved binaries can be straightforward if you just model set of binaries, try to see if you see them or not, and you can test different assumptions and see what works. Maybe similarly to your basically to what you saw with the brown dwarfs, you can maybe rule out all kind of crazy things in the literature already. And based on what you showed us, maybe it also has some connections with one of the inflection points.
Yes.
There is a relationship between mass and multiplicity, or the likelihood of being in the multiple, and maybe you can see it. So
yeah, those are all good suggestions. Yeah.
There's a question on
Oh yeah. Would you mind reading Brad's question?
We can all read together maybe.
Is there any difference? Any evidence of a difference in the IMF between single stars, stars in multiple systems?
I don't know, at least not for the 20 parsec sample, because the paper I submitted just on the individual IMF was already 125 pages, and I decided not to go into multiplicity statistics. I left that for my colleague Daniela Bartolez-Galiufi, who's at Amherst College, to work on, and she and her students have been working on that for the past year. And I've not seen the results of that yet, but they were going to start some telecons here, I think, next month to tell me what they found so far. So I guess they stay tuned.
All round doors are rejected for, none would be in binaries, right?
I think that would be reasonable, yes. Yes, Your Honor.
I have a question.
Yeah,
What's your problem with logs? Why don't you like logs?
I don't think in logs, and I have to use magnitudes all the time. It kind of annoys me, and I think it annoys a few other people in the room too, but.
So what's yeah, so why should we be making histograms in linear units of things that span?
I wouldn't say I'm encouraging people to always use linear units. It's just that if you're saying that something's peaking at 0.3 solar masses, you need to make it clear that you are binning in log when you say that. Because I think some people have taken that statement at face value and not realized that there's a log component in there. That's really all I'm saying. So.
All right, Mike.
Microlensing surveys have found evidence for substellar objects, and I was wondering if there's now enough data to kind of connect the substellar from the microlensing surveys to this work.
Yeah, Zdeněk Mróz was at Caltech for a postdoc a few years ago, I think just at the beginning of the pandemic, and he and I talked a little bit about this. And the mass function slope he was getting out for the brown dwarf component in microlensing was 0.6 or 0.7, so it's almost exactly identical to what we were finding. Yeah.
Ben?
How many white dwarfs are there in your survey? How many
Between 200 and 300, I think.
So, so if there were, going back to this question that came up about maybe losing the high mass ones, so there'd probably be maybe 10% or so that we're talking about, that might be coming from high mass stars that have been 10% of the total number that have disappeared. But how many stars are there? A type stars, B type stars that are say within 3 to 7 solar masses and now on the main sequence in your survey?
No Bs. I think there are a few As.
So it seems a little, to me, it'd be a little strange to have only a couple of A-type stars that would produce relatively high mass white dwarfs, and yet have a significant number of high mass white dwarfs that would have missed, given how few relatively high mass A stars.
Yeah, if we look at this diagram here, this is showing the actual mass estimates for the white dwarfs when they were on the main sequence. And the highest mass I have is when it's 7. Then there's another skip down to 6.2, something like that. There's a couple, maybe 4 objects down there, and another skip down to 5.7 or something. So that's what the distribution looks like.
Wondering if you could go back to your Gaia HR diagram there.
Okay.
Because I'm not that worried about missing white dwarfs here.
I wasn't before this talk. Where is it?
That was pretty early. Yeah.
One more. This one?
Well, yeah, I would go back to the Gaia one. So the faintest Gaia white dwarf you have has a Gmag of 16.
Mhm.
And Gaia's sensitivity limit is obviously below 20th there. So for you to have missed white dwarfs, there'd need to be no white dwarfs between 16th and 20th, and then for there to be a population under 20th. So I think they're just so close that you're finding them.
I mean, I'd love to talk to Ben at dinner about this a little bit more, just so I understand. Okay.
Say something similar Hour ago, maybe I said it more clearly. That's the point I was making then
Okay.
too.
Okay.
You wouldn't have this huge gap if there were a whole bunch of others that are just out of sight or something.
That makes sense now that Eric's explained it. Thank you.
By the way, just so people know that Davy was a postdoc here for the better part of the year, 20 or so years ago, and Eric and Davy and I wrote a paper together on the first, trying to understand something about the first ever detected L-type object, GD 165b, that Davy led that effort. That was about 20 years or so.
Awesome.
More than
Let's-
20 years.
I think we got one more question in the back.
I'm gonna go for it, and I wasn't sure how you picked the 5 masses of Jupiter as the limit for your example. Could you go into that?
Yeah, so we had a couple of papers prior to this one in 2024 where we tried to figure out what the low mass cutoff was just based on the brown dwarf sample. And we looked very carefully at the brown dwarfs within 20 parsecs that were part of a young moving group. And that in those cases, we can actually attach an age to those brown dwarfs. And based on the individual brown dwarfs we were finding there that were parts of moving groups, we know we had ones down to about 5 Jupiter masses. So that's how we kind of set the lower limit. Although I really couldn't tell that from, the brown dwarf population in mass, because I don't have ages for those, and the histogram was kind of chunky. But yeah, 5 Jupiter masses is about as low as we can go with the 20 parsec sample. And I believe Ray J may have come through here with a colloquium a few weeks ago. And I believe his JWST data was poking at maybe like 4 Jupiter masses as the lower mass limit. So with some caveats there, but so we may be close to where the end is, if there is an end, unless they do a white dwarf thing and get really cool really fast.
All right, let's leave it there. And thank Davey again.
Oh, thank you.
Right, Neil went in.
Yeah.